All right. Everyone, please welcome our friend and partner, Jensen Huang. Thanks for being here, man. All right. So,
I've got to be the most uncarrier guest you've ever had.
well, you've got your characteristic leather jacket today,
I like your jacket,
which is great. AI ran. Who cares?
Well, my gosh. Let's take a step back. First of all, in 2016, we introduced a brand new type of computer called DGX-1 and reinvented computing after 60 years. And the impact of DGX-1, which is now a well-known AI supercomputer, and it's powering AI all over the world, is changing the computer industry, revolutionizing how software is done and what software can do. And it all started with the invention of that system, the processors, the software layer that went into it. At the time, nobody knew about that software layer, but it's called cuDNN. And it's based on this algorithm for deep learning, but for this architecture we call CUDA, and which evolved into Cutlass. And these underlying libraries revolutionized artificial intelligence, democratized it, put it in the hands of researchers everywhere. And today, we're announcing a revolutionary new computer. And this revolutionary computer is called ARC-1, aerial computer. You saw just now an image of it. In 2016, I delivered it, DGX-1, to OpenAI. I was hoping to deliver ARC-1 to you today. However, I learned that it's been shipped to you already. And so unfortunately, because we're not in the same city, I don't get to deliver it to you personally. And so it's on its way to Seattle to power the laboratory that we're building. And really what's happened is we created a new computer, a brand new type of computer that fused radio processing, insanely complex wireless algorithms. And most people need to understand the wireless communications. The spectrum is limited, the algorithms are complicated, the environments are diverse, dynamic, electromagnetic radiation is not a simple physics, and yet you're trying to optimize the quality of service for everybody, manage the spectrum, manage energy efficiency.
Yeah, this stuff's harder than it looks.
Oh
right?
my gosh,
massive. We all take this for granted. We go around with these incredible computers in our hands, and by the millions, we connect it, to vast quantities of data being sent down at hundreds of megabits per second, no matter where we are. And in real time, the computing power to give each of us the signal we need, it gets harder and harder and harder the more we use. And so this is all about getting more and more performance from each unit of frequency.
And for the very first time, we're going to bring artificial intelligence to it.
So let's talk about that, because the video showed, one of the case studies in the video was kind of trying to demonstrate how a radio has to do the job of optimizing its performance given the real world it faces. And every radio faces a different piece of real world. The shape of each of the world around each radio is different, and it's not static.
That's right.
It changes in real time as well. And yet you expect your signal to be perfect at all times, even though the world is moving and you're moving. So how does AI help with all this?
We're going to have to create a brand new type of computer, and the computer we created called ARC-1 fuses radio processing and artificial intelligence processing into one platform. And so as a result, we have the ability to do two things. We could apply all of the deep reinforcement learning algorithms that we use for robotics. We could teach these AI models how to optimize signal quality in hundreds of thousands of virtual cities that we showed you. Then when we finally put it out into the real virtual city, then that real city becomes the 100,001 scenario. And so it's already learned how to optimize across so many different scenarios through domain randomization and simulation in these supercomputers. Now the next version, the next one in all these different cities and different environments, it would have been optimized before. And we're going to use similar algorithms that we use for robotics. And so robots have to deal with very complicated environments, and reinforcement learning does that. AlphaGo uses reinforcement learning. Many reasoning systems in the future, AI reasoning systems, are going to use reinforcement learning. Robotics uses reinforcement learning. So we're going to use very similar techniques that allows us to enhance the delivery of services using a lot lower, hopefully, spectrum energy and reduce energy efficiency. Meanwhile, that same base station, that same computer that is now all over the world is an AI computer that can host AI traffic. And of course, the amount of traffic that is in any particular radio changes throughout the day. And whenever it has more computation resources than is necessary for the traffic, we can utilize that for additional services for T-Mobile.
Okay, so non-RAN workloads at the edge near the customer is what you're talking about. I want to come back to that, but first I want to sort of because I know we're geeking out about this, and you know we have the world's most important telecom investors and investor analysts in the room and online, and I want to try to make this kind of real about dollars and cents and customer experience for people. There's been a trend for a long time that we're moving in this industry towards a more open RAN architecture, towards software-defined RAN, trying to get all that sort of technology out of the radio and into the cloud for obvious financial benefits, efficiencies. But that has proved kind of elusive at scale around the world. How can accelerated computing of the kind that Nvidia produces with this new product make a difference and finally make some of these promises of virtualization of RAN technology into clouds a reality?
Software-defined networks, obviously a wonderful thing. However, the radio network is just so intensely computationally intensive, and to do the signal processing, to do the error correction, insanely hard. Massive MIMO, insanely hard. And so the first challenge is, how do you move to a software-defined environment where Moore's law has really run its course, the CPU can't keep up with the workload of an ASIC? And so the answer, of course, is accelerated computing, using CUDA to do that. It took us 5 years to create the Aerial library, which allows us to use CUDA to accelerate 5G radio and prepare for 6G radio. The second thing is, of course, once we do that, then the computation stack can also support AI. Now we've fused signal processing and AI into one computing platform. Your radios are going to be extraordinary 5G radios and be prepared for 6G in the future, as well as an AI computing platform to deploy, to host, to run AI on it. And the AI could be used to, of course, improve the efficiency of the network itself, as well as, of course, host brand new AI services like the ones we showed in the video.
So I can tell you why we're interested in all this as a partnership, and then I want to ask you why you're interested in working with us. But it's very clear to us and to most objective observers how far ahead NVIDIA is in leading the accelerated computing transformation around the world. And for us, as we think about how that applies to our industry, it's going to completely change network architectures. And so, you know, this 5G chapter that we're living in is several years old now. We're thinking about what's next, and we're thinking about how to get there in a highly cost-effective way. And that obviously means we've got to think about virtualizing the technology, put it in the cloud. And there have been barriers to that you just talked about. Traditional computing just can't keep up with the ASICs that have traditionally been deployed in non-virtualized, non-software-defined RAN environments. And so for us, you know, our view is that if we can be co-authors of this transformation, we can have our engineers in there deep as not passengers on this train, but conductors working with the world's leader, like NVIDIA, like Ericsson, like Nokia, to create the future. T-Mobile customers will benefit disproportionately. That's our belief. And we have that belief because that's exactly what unfolded in the 5G era.
Yep.
And that T-Mobile customers will get it sooner, and they'll get it better, and they'll get it more cost effectively. So we are very excited about inventing this future with you. There are 300 operators around the world. Why did you decide to work with T-Mobile?
Well, first, you made a huge difference. The fact that we were talking about this vision, you know, we're in the process of reinventing the automotive industry from a car industry to a technology industry that's software-defined. They had the same challenges going to software-defined ASICs, and yet they would like to move into a world that's accelerated and powered by AI. We've seen that with medical imaging. We've seen that of course, we're seeing that right now in robotics. Our first meeting, we connected the dots almost right away. And you saw the vision of the technology. You offered the massive might of T-Mobile and the incredible engineering team. Wolf and the engineering team leaned right into it. I think we all saw the same opportunity to reinvent telecommunications with the fundamental technologies that is reinventing one of the largest industries in the world, which is computing. And so this underlying technology will unquestionably revolutionize every industry. The fact that you jumped onto it, you personally jumped onto it, drove the conversation between our two companies, and then now our two engineering teams are working so intensely, closely together, launched this new innovation center, start deploying infrastructure so that we could develop the software, get the software ready, industrialized, optimized all over the world. It's going to be incredible.
A minute ago, you started to talk about a secondary benefit of all this that has us very excited.
Yep.
And I want to explain it. The idea of when we virtualize our RAN technology into the cloud, working with the world's leaders, what we will realize is that the same thing will be true of those workloads that's true today of mobile networks, which is the demands against each individual component are highly variable, leaving massive underutilized compute power at all times of the day and dispersed geographically.
That's right.
Sometimes it's taken up by the workload of the RAN, and sometimes it just sits there. And this creates an actual business opportunity for us.
Right.
We just talked with Sam Altman about the rapidly unfolding technologies in AI. And one of the things that AI requires, especially for the kinds of things we're demonstrating in this video, is incredible latency, right? Fast response times, because AI is moving from its traditional formats of like text. I'll text you, you'll text back. No latency needed. But when we're responding in real time to videos and face intonations and working with avatars, that's going to need to be incredibly responsive. And the AI workloads of the future will need compute power in the network close to the customer. And the very compute power that we're going to build together to support this RAN capability could actually also compute secondary workloads for our customers.
It's exactly the same computing system now. We've fused radio computing with AI computing into one architecture, and we call it ARC-1. And this computer that we built is extremely low latency. It's CUDA at extremely low latency. It has the ability to deal with time-precise transactions, all of the things that you need to provision high-quality voice services. Now, one of the things that people don't realize is that the world's wireless networks are extremely over-provisioned. And you're over-provisioned because you have to deliver such extremely good quality of service when somebody needs it. But when somebody doesn't need it, that infrastructure is sitting there and it could be reutilized. And so when we made it software-defined, made it accelerated, made it able to run AI processing, we now turn that entire network into excess capacity when you need it for excess opportunities. And so this is going to be a great new growth opportunity for the telecommunications industry.
I love it. We have a few spare minutes, and so before we let you go, let's just change the topic and talk about what you're excited about. One of the things that...
I'm excited about reinventing the telecommunications.
Yeah. Well, you guys have...
I don't know about you guys, but...
You guys have an incredible
This is a giant growth opportunities for both of us.
Yeah, it is.
For both of us.
You guys have an incredible lens on this entire revolution because literally everyone at the forefront of AI are working with you.
Yeah.
And so as you think about how this most transformative technology in our lifetime can really change people's lives, like what gets you excited? Like what's Jensen see in terms of how AI is going to impact all of us?
Well, we're all going to have a whole bunch of digital agents working with us. And I really love the idea that I will have a computer that is getting smarter and smarter with me as it works with me over time and understands me to help me get things done. And I love the idea that I'll have my own R2-D2, my own C3PO. And my R2 will be following me. For many people who are just growing up now, they're going to have their own personal R2 with them for their lives. And that R2, of course, could be digital versions of it. It could be a work version of it. It could be a physical version of it. I mean, the idea that all of us would have that, whether you're a scientist or an engineer or a philosopher or just a person, we're going to have all of these amazing agents that help us, along with our lives. Now, one of the things that Sam introduced recently, the reasoning capability of these AIs are going to be so much smarter, but it's going to require so much more computation. And so whereas each one of the prompts today into ChatGPT is a one pass, in the future is going to be hundreds of passes inside. It's going to be reasoning, it's going to be doing reinforcement learning, it's going to be trying to figure out how to create a better answer, reason a better answer for you. Well, that's the reason why in the Blackwell platform, we improved inference performance by 50x. By improving the inference performance by 50x, that reasoning engine, which now could take up to minutes to answer a particular prompt, could still now respond in seconds. And so this is going to be a great new world, and I'm excited about that.
What do you see happening in terms of power consumption? This is one of the most talked about aspects of AIs, the carbon footprint.
Well, we have to use AI to reduce energy consumption. We know now that we can do climate prediction, weather prediction, 10,000 times more energy efficiently than using classical supercomputers to do so. Moore's law has really run its course. We have to use a new type of approach to go figure out how to do these computation. The work that we do together in data processing at T-Mobile, if not for accelerated computing, how would we reduce the amount of energy consumed and the time consumed, the cost consumed by 20x? And so everything that we accelerate, everything that we teach an AI model to do, will do a lot more energy efficiently. One of the examples I use is my puppies don't know Newtonian physics, and they don't understand the trajectory of balls from the concept of simulation. And we know that the world's first supercomputers were created to simulate the trajectory of missiles, and yet dogs have no trouble after some practice snatching a ball right out of the air, sometimes a mid-somersault. And so how did they do that? It's the same idea. And so we're going to teach AI not to compute weather through multi-physics and thermodynamics and fluid dynamics and convection and conduction and ice science and ocean science and such. We're going to teach it to predict it. It doesn't completely understand the causality, but it predicts it wonderfully. We just want to know what tomorrow's weather is going to be like. And so so that's one example. We want to do the same thing with radio networks. We understand the principal physics of electromagnetics. We understand the principal physics of how radio beams reflect, refract, deals with different environments and so on and so forth. We understand beamforming. We understand the physics of it. But yet, when you operate that network, you're just trying to deliver a better quality of service at lower energy, higher throughput for more traffic, lower cost, lower energy, so on and so forth. And so you don't have to do the fundamental physics simulation anymore in real time. Just use AI to do that. And so this principle of simulation to understand first principles, how things work, causality, and then using AI to emulate that fundamental understanding reduces energy tremendously. And so people have to realize that training models take a lot of energy, no doubt. However, the goal is not to train models. The goal is to use models. And that's going to save tons of energy.
So it's just so exciting. And there's a big opportunity in this for both of our companies. The bottom line is this: billions of people around the world are connecting it every second of every day to millions of cell phone towers. And that technology has the opportunity to understand the physical environment that they're operating in while they're in motion and while the world is in motion, and use advanced AI to predict exactly what signal will reach them best in order to give them the best possible experience at the lowest cost. That is, given the scale of this industry around the world, that is a massive opportunity for Nvidia, for Nokia, Ericsson, the other partners in the alliance, but also for T-Mobile as a co-author of all this, in working with our customers and potentially with our peers around the world. This is an exciting moment.
And Mike, for us, it's such a joy. It is very rare that we have a partnership where our technology and our know-how could be useful to you in how you run T-Mobile, but also in the technologies that enhances future products, but also expands the market opportunity together.